Hey, what's happening, everybody? How are we doing? 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 Hey, what's happening, everybody? Oh, sure, you guys heard that like I heard it too. That's why I listened to the stream. That's why I've got a struggling a bit with the homework. Let's take a look. Let's take a look. Which shout out the question you want to talk about? Let's start talking about those questions. Sometimes when I have the stream on the background. So that's what happened. Why are you being weird, R? Which is this? I think Andrew. So Andrew's got first here. He's 474, and then Kelsey. Is that also 474? I think that's also. I think Kelsey's 474 also. I think. Correct me if I'm wrong. Good. And then we'll lead into 2C and 2D. So 2C, we're doing a little model building right here in 2C. Okay. We will skip trying to estimate the predictors since they're still a tremendous number of columns rather than, okay. So we have to clean up the data first. This is the NFL data, I believe. And the first step with this, which I believe we did already, it has you do all this first. We talked about this. Check out Thursday's stream, yesterday's stream, yeah. We talked about what all this means. So if you're looking for a really in-depth talk about what every single one of these means right here, I went through and I made data frames to show what near zero variance. We got that, Brad. You got it. And we talked about all of these right here, removing out the near zero variance and all of these. I think, let's run all the code above. We'll hope that everything works. We will hope we don't break it. Yeah, this can make a data frame. That's fine. See, we got a, we want the EX. We're still calling it, are we calling it NFL? We're calling it EX3 NFL. What is the name of the data frame? And we're calling it EX3 NFL, right? Cool. And yeah, there it is. Okay. So it's removed out these right here. It says the NFL for the rest of the problem. Are we using NFL? I think we might call it NFL 1 point. Here it is right here, where we load it in, we scan in the wins, we attach it to it, and all that stuff. In question 2B. So this is defining the linear combos right here. This is storing team as null. This is writing, yeah. So this right here, we're just gonna remove out, and then we should have, cool. Yep, we're good. Okay, we got the right data. It's all set up from question 2A and 2B. It looks like the data is set up the way it should be. We've removed the linear combos. And the mean for that one, what do you mean the mean? What do you mean the mean? It says in 2B. So you'll see the data from now on. What fraction of rows are missing values in FNO? Oh, what fraction of rows are missing for NFL? So what fraction of rows are missing? What do you think we should do here? How can we find missingness? How is missingness found? And a few people on the midterm take home, I was like, oh no. Well, I don't think it's complete case because let's take a look right here. It says, what fraction of rows are missing values? Actually, yeah, that's right there. That'd be right. Jordan's right. Yeah. Sorry, you were right. Complete case is the code. Complete cases, we can look at NFL right here. And we can go right here and do what around it. That is 100% right. Because what fraction of observations are missing would be is.na. So we'd get different answers right here, and I'll change it to the other one. What do we put around this now? Because complete case, what complete case will do is it'll tell us if a row is a complete case, which I think we're good now. And if it wants to know what are missing, whoops. Well, complete case is a logical, right? So this is a logical vector, and we need the mean of the logical vector. So if these are, so yeah, let's do this. Did you get that they're all complete? Everything's a complete case? Is that what you got, Jordan? Just making sure everything's right with mine. That we don't have any missing. Yeah, so we're good. So, like, what does this mean? It means that there is no missingness, which we could check. We could do is.na, and this will tell us if things are not NA. And so you could see what is NA, and there's no NA data. So either way, there's no missingness in this data. Which is good. Remember, we started off this class by talking about missingness, and so I wouldn't technically do. You're going to get the same answer kind of both ways because the data has no missingness. And what do we mean by this? We mean that there's an observation everywhere. There's no NAs in this data anywhere. So interesting enough, you get the right answer either way, but by asking what fraction of rows contain missingness, it's complete cases. And we could confirm this really quickly. We've got some data frames built that we can kind of mess around with. If we look at this data frame right here, this is a theoretical data frame. You can see its structure. Now let's look at it. What fractions of rows right here are missing data? What fractions of rows are missing data in this data frame? What fraction of rows are missing data in this data frame? 20%. So we should get 20%. So we can confirm. So if you look at the way the code's working, now here's where the difference comes into play. If we use the is.na, we're gonna get 4% here. Yeah. So the difference between these two codes is this code right here tells you the overall fraction of percent of NA in the data frame. It tells you the percent of missing values in the whole data frame. This code right here tells you how many rows do not have complete cases, because it's how many rows are not complete cases. The not right there flips it. So does everyone see the small difference right there? Does that make sense between the code right here is what fraction of rows are not complete cases, and the code right here is what percent of the data frame is NA, what percent of the whole data frame, and the whole data frame, 4% of the whole data frame. And we can see the visualization of what we have right here. When you're asking about the rows for complete cases, it identifies this one as the 20% we see right here. So kind of just knowing what the code does is important, and being able to like visualize how it would work out. Like we always want to be able to solve a code in our head, like a smaller version of it. And yeah, and that's why I have these examples right here, because it kind of helps to see it. So we've got it. You'll skip trying to symmetrize the predictors since there are still a tremendous number of columns. Roughly 8% of your time is data cleaning. Let's split the data into training and holdout. In this case, you're doing, okay, so this is where we make the before 2011 data set. We need to make a subset right here. So we're going to split on year. So what is the format of subset? Like what goes in subset the first thing? The first thing in subset is what? How would you explain, if you had to tell someone what to put in there, what would you say to them? Pretty much. It's what do you want to subset? And we want to subset the NFL data, right? Then the next thing that goes right here are the whats. And it could be multiple. It's just going to be one for now. But the next thing we would do is, well, it is going to be year. And you are correct, Andrew. You're 100% correct. It is going to be year, and I believe it has a capital Y. We can confirm down here it has a capital Y. And these are all the whats for how we're going to make our subset. I believe it's less than or equal to, right? I believe it's that. From 2011 and before. Cool. So we'll call this sub. Doesn't want to. Oh, we're calling this train. So everything right here after this comma is all of our starts with a C. It's like when you're, I don't know, trying to think of a way to like, I think of it as filtering criteria. Yeah, exactly. Yeah, it's all your conditions. I think of it as the conditions. And you could say like, and this, where's, you know, I one of these just learn where and is that. It's like the one button that doesn't glow as brightly. And then you could say and this, or this, or this. Then when you put a comma, it drops down to here and you're in the next argument. Now I'm just writing nonsense right now, but I'm showing that we're kind of in a sub state of the arguments. And we do have a train right here to check. And it looks like we're pretty good. Yep. If you look at the bottom here, we're pretty good. We've created what we need to create. We've created the train. Using the train, fit multiple linear regression models on train. Remember to have pre-proc. So we've got our cheat code down here already. So we've already got this right here. So we're just going to grab this code as is, and we're going to kind of talk about, what about the holdout? Oh, we need to make a holdout. Andrew, 1,000 points. Let's go make that holdout. So what we could do, because we need, does it give a check for the holdout? And it says make the holdout, right? So if we want to make a holdout, we're going to copy our code. Cool. Let's copy the code. Let's drop the code. Not there. Let's drop the code here. Holdout. And we want greater than. There we go. Holdout is made. We have data to test it on. And I'm out of coffee. So we have a dichotomous data set. We could confirm that the holdout is also good. 32 observations, because I think it's 2 years. It says 2012, but from year 2013. Wait a minute. Does that have a typo? In fact, we are going to use the year 2012 with information on wins in 2013. So let's see here. Oh, yeah, okay, yeah. So it's the 2012 season with wins from the 2013. So it's 20. So it's just saying like I think it's saying it's like has information from 2013, but the season was the 2012 season. Like this is the 2020 season of football. So it would have data going into 2021. So it's confusing, but I think we should be good. I think so. Maybe not. Maybe I broke it. Ah! So it's important to know the format here. And I think this is the code we're doing for the next one, but we do need a fit control also. So let's go down here and let's grab a fit control. We already have written a fit control today for this. Where's our fit control? Here's the fit control. So, and I'll drop the fit control in the chat. Yeah, so it says 2013, but it's 2012. So it's like it's the 2012 season, but the file says 2013. It's super confusing, as data often is. And let's go right here. Let's drop this in, and let's take a look at what's going on right here. So the fit control does the what? The fit control controls the what portion of the data. These are quick and easy test questions like that. The fit control controls the what portion of the data. Things we need to know instantaneously. Like, what is the whole point of the fit control? I wish I could do a written response and just say, explain to me why we do a fit control. So it controls this, which that in turn leads to us doing certain things. What is the point of a fit control? Why do we need a fit control? Why do we need to control how we fit our model? So that's what it's literally doing. It's controlling how we fit our model. And why do we do that? Who has any ideas in here? It's a really good question. And this is the theory stuff we need to understand, where we build our knowledge and we say like, okay, this is what we're doing and why. Why do we have a fit control? Because there's 3 portions of our data, right? We actually just built 2 of them. This is controlling that middle portion, which controls how we pick our model. And how we pick our model is based on the validation portion of our data. And this is the k-fold cross-validation process right here with 5 folds. So this will do it all for us. We don't have to actually do it. It will manually k-fold cross-validate the data. I think there's ways inside of Caret 2 to create trainings and holdouts. We just have you manually do it so you can practice it. I mean, there's always more code. Everyone is improving code every day. But if you understand the point of it, and it's not that hard to write the code for it, but so there's shorter versions. It's like, oh, you can save 10 seconds, but practice. So we make a fit control right here. Now the point, we could make this over here. You could take and drop this right here. It would do the same thing, but it's just too much. So we don't put it there. Is Brad still here? Because guess what? Y tilde X comma data equals classic right there. So when you learn that in 320, when you learn Y tilde X comma data equals, there it is, Brad right there. Y tilde X comma data equals, just like Y tilde X comma data equals. So whatever your data frame is. Awesome, Brad. 1,000 points, Brad, right there. So if you notice, this same format right here is being used with the train Y tilde X comma data equals. But now we have more arguments. We have argument here, method GLM. So what are we doing? Are we doing elastic net? Are we doing lasso? Are we doing ridge? Are we doing regression? Are we doing logistic regression, which 320 just heard about today? What are we doing? Vanilla regression, yeah. Which means we're not doing a regularization procedure on it. We're just doing good old normal regression that 320's been doing for the last few weeks here. So we're just doing regression. That's all we're doing. This stands for generalized linear model. So that thing I had just written with LM, you could literally change this to GLM right here. So, and I was showing that to the students today. You can do GLM instead of LM, and we'll do that for binomial models or logistic regression. GLM just stands for generalized linear model. It works for linear, and it also works for logistic. It's just that LM only works for linear models. GLM works for both. So you're like, why don't we always use GLM? Well, I don't know. That's a good question. It's like LM is just a quicker way. It only uses family Gaussian. The TR control equals fit control. That's controlling right here. And the preproc center scale, favorite thing, what does that do right here? Preproc center scale turns everything into, say it for me, you guys know it. You gotta say it, you gotta say it. Preproc center scale turns them all into, favorite thing from 201, your next year's wins can't be found? Dun, dun, dun. That means the training wasn't made properly. Z-scores. Let's see if mine works. Well, okay, mine works. Do this, Andrew. Double-click train, run it, and see what you get. Does anything show up when you double-click train and run it? Does anything show up when you double-click train and run train? Does anything show up when you double-click train and run train? Does anything show up or no? And if it doesn't show up, go back up to where train was created and make sure you're passing the standard. It does? Then check how you spelled next year's wins. Take next year's wins from here, double-click next year's wins, and make sure you've spelled it properly. So if it says double-check how next year's wins is spelled, and then double-check how you have train right here. Make sure you have data train, because you might not. It's got to be an error here or here. One of those right there has to be the error. It has to be one of those. And tell me, you can drop your code in the chat if you want. Yeah, there you go. No S. You didn't have an S on it. It had like next year wins. Oh, I see it. I see it. Yeah, if I take this right here, you'll notice one of the best things you can do when you learn these small little tricks is, I'm trying to grab it and it's going too much. One of the things you learn with coding, this little trick right here, that if you have something written, if you double click it, it'll highlight all other instances of it. And so if I double click this, it shows me it's spelled the same way. So just little checks we can do. So here we are with the vanilla, just regular old regression. And I think we got it. So we can just look at how the model's doing, which I think was the point of it. Filter multiple, look at the results. And we've already got some codes for this. We got the sanity check right here on the model. So we can take a look at it. We'll do it without taking the code. And did we get it? Let's do GLM results. There we go. And that is the same number right there. So the GLM only has one model because it doesn't have fitting parameters. So it's just going to fit the one model to it. And what is the main number we care about right here? What is the main number we're going to clue in on? What is the main number we're going to be like, okay, that's the number we care about? How do we judge this model? I mean, there's multiple ways. There's 3 ways, but we choose one of them. What 3 ways could, what is the one way we'll judge this model? We're like, this is how good the model did. RMSE, yep. Typical miss the model makes, and we go right here. We look at the RMSE, and we just record it. I mean, that's what we're going to take down about this model. And what's really awesome is from here, you know, like, you can fit so many models. You really don't even have to, you know, truthfully know that much else. Just to show you one real cool trick, and we're going to hop around because we're going to probably hop to Brad's question here in a second. But watch this. Caret models, and if you go right here, let's go to SVM. There's so many support vector machines. We should be able to make an SVM. It's got C, which is the cost, and lambda, which is the regularization. Support vector machine expo string, and then there's support vector machine linear. We could do that. Cost, I'm trying to think what the cost parameter goes through. We could just do an SVM linear. So if you want to try a different model that you've never tried before, you could go right here, and so now we'll need the tune grid argument for it, which is the tune grid's going to be right here. We'll use tune grid inside of here. And so this is a model that we've never even seen yet. But if you were to look up all the things about the different parameters, and so put that right here, put the comma. So you could get SVM linear, drop that in here. Now we need we'll go SVM grid. And the SVM grid, there's only a cost to it. And I think the cost, expand grid. There we go. And let's say C equals, let's go sequence from 0 to 1 by 0.1. And that's got the expand grid. And I think everything's right. We don't want to save it into GLM. SVM, let's go SVM model. Yes, we'll download the package. Cool. And it's going to like it. It's doing its thing. And this is the beauty of kind of having everything available in Caret. And is it doing it? Package kernel lab. Okay. We'll let it do its thing right here, and we will load up. And then we'll look at Brad's question. And the best model to use would be the one with the simplest. Yeah, that's what we generally do, is we take the simplest model. Are you doing all right? One package is needed for this model to be installed. Kernel lab, would you like to try and install it now? Kernel lab successfully unpacked. Oh, is it really? The model might be taking this long to run. Whoa. Support vector machine's pretty crazy. It puts a hyperplane through the model. So I actually think that the model's running. I think the support vector machine is just taking a while, and I'm actually kind of interested. Here, we'll take a look at, Brad, which question were you working on? We're going to let it try to do its thing here on the support vector machine, which is just craziness. Good thing I didn't do like a polynomial kernel on the support vector machine. I shouldn't have done that big of an expand grid, should I have? Let's stop this. Let's do by that. And yet, was the support vector machine running? So that should cut down a lot of its time right there. And the best model 3, I think it's pretty basic, but it's just running right now. No worries. Here, we'll see what's going on. I don't know if I have that one downloaded right now. Let me go and get that assignment. We're just gonna let this run in the background while we're doing it. Let's go and check it out. It's just gonna keep running. This is why even amazing computers these days require, like you're gonna just tax your computer. Computer's gonna be like, oh, it's too much work. Can't complete all the work. So we might have to say no to this support vector machine model. Okay, question 3. We'll see if this eventually does this thing. Question number 3. Wait, am I going mad, Brad? Here we go, question 3. Okay. There have been interesting studies that look at the association between someone's income and his or her attractiveness. A recent study found that more attractive real estate brokers tend to make more money. Imagine predicting the selling price of a house based around whether the agent was attractive. Treated as a categorical variable, yes, no. Since the selling price of a house depends on many other potential factors, explain how you would isolate the association between selling price and attractiveness. This question is intentionally a little vague, and you should not feel the worry to give more than a few sentences. Okay, so there's a key thing that multiple regression does that we should know instantaneously, and it has to deal with, yeah, we'll do it. You got it, Alexa. So what does multiple regression do? What's the point of multiple regression? Like when we do a multiple regression, you're saying F in the chat for the support vector machine model. The point of multiple regression, what can it do for us? Like multiple regression, when you put everything in the model, what does it do? Oh, look at that. Look at all these errors. What did it do? Warning, 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 warning. It didn't like that C equals 0. What does multiple regression do? There we go. Oh, yeah, I shouldn't put in 0. Well, darn. All that for such a horrible thing. That was useless. Yeah, I guess you can't put in cost 0. Theoretically, that wouldn't work. So when we do, so these models weren't even worth it, Jordan. It was the models I did. No, not even worth it. So when you do a multiple regression, it isolates the variation. So think about this. We could collect data on people, right? So let's collect a model. And we have a model here that has the variables. Let's do here. Let's clear out. We didn't get a good support vector machine. We have a model that has data on like attractiveness. And someone says to you, I think it's attractiveness. It was bad, right? Did I miss it? It was higher than all of our other RMSEs, right? I deleted it off, but it was higher, right? It was bad, right? That's why I was like, okay, that's bad. It was like 3.8 and 5 point something, or yeah, good. I thought it was like 1.2 or something, and I was like, oh no. I know I could do the polynomial kernel and try something different, but you just kind of throw everything at the wall with these types of things. But yeah, I thought it was good for me when I was like, I thought it was bad. Okay. If you're looking at attractiveness and you're trying to see if that plays a role in whether or not somebody like does a sale and how good of a real estate agent they are and how much money they're making, someone might be like, they might say maybe attractiveness plays a role, but how should we compare? How should we compare to real estate agents? Like, imagine this. People who work in LA, I'm not saying they are, but let's pretend, are more attractive. Does that make sense? Versus people in, try to pick a random, Bath, New York. It's where a place I used to live. Nothing against Bath, New York. I was like, where's a place I could pick on? Okay, Bath, New York. Sorry, Bath, New York. So we got people who do real estate in Bath, New York, and people who do real estate. I don't know if that's a real place or not. I'm not from there, so I'm not going to comment on it. Population 43. So you know, when you think about the LA market, you've got all these like supermodel people selling real estate, right? So who's to say it's their attractiveness that's, you know, the reason that they're making so much money, or maybe it's where they're selling? What's the point of a multiple regression? What is the key phrase we say in multiple regression that would come into play here? Because if you're like, is it their attractiveness, or maybe it's their location, or maybe it's the years they've worked, or maybe it's their number of clients. So when you look at all this right here, and you think it could be all of these things, like what's the point of a multiple regression? Like what is the key phrase in multiple regression? Right, like right there. Isolate, and Andrew's right also. You're isolating the variation because it's two otherwise identical individuals, two individuals who are otherwise identical. So you're saying these people have the same market, they have the same years in the industry, they have the same number of clients, but one is deemed attractive and one is deemed not attractive. So we can isolate the source of variation on attractiveness. And that's the whole goal of a multiple regression. Like this question is so key because it's the whole goal of a multiple regression is to isolate the variation and say, okay, does attractiveness play a role, or is it something like somebody's years in the industry? And we saw this today with, I think this one right here. So we saw this today with the piercings and stuff where we had the variation go away. So we were talking about, here it is right here, where we have a correlation between weight and body piercings. Here, we'll hop to lecture screen. So we have a correlation between weight and body piercings, but it's just due to gender. So when you control for the variation in gender, the association between body piercings and weight is no longer statistically significant. You can see here the p-value goes away, where previously this was very, 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 very statistically significant. There was a statistically significant relationship, but what did we do? We controlled for the lurking variable, and now with gender in the model, number of body piercings doesn't explain anything because number of body piercings was associated with gender, and it looks like gender does a better job explaining someone's weight than number of body piercings. So how do you control for someone saying, well, maybe it's that the people are this? You'd be like, okay, well, let's put that in the model. So anytime someone says maybe this variable is a factor, you put it in the model. Now here's what irks me, is anything that's outside the model is assumed to have a coefficient of 0. You can't say, well, I think it's this, and you'd be like, okay, I guess it's that. No. I mean, you could make an educated guess and then do research, but you don't have evidence of a coefficient until you have the variable in the model and you figure out that it has a significant impact. Like now we know that this coefficient is unlikely 0 because we have the small p-value here to suggest that the variation attributed to gender male when explaining weight is statistically significant, even with the inclusion of number of body piercings. And we could do gender male by itself, but in the multiple model, gender male brings with it additional information that the other variables are not accounting for. It reduces the sums of squared error with the other variables in the model. So that is what's going on right here. Does that make more sense, Brad, for this question? I saw Alexa had a question about question 1D3. So we would look at the scatter plot. What we would do is we would put all the variables in the model, and at that point it gets a little hard to graph it. So anytime someone says to you, like, I think it's this variable, you just put it in the model. So when someone's like, well, maybe it's due to this, and you say, okay, let's put it in the model and see what it does, because the model will control for it. Oh, awesome, Alexa. That's so good right there. The model will control for the variation. So when someone's like, I think that weight and body piercings, I think it's actually due to gender. You're like, okay, let's put it in the model. Oh, look, it was due to gender because gender is now significant and number of body piercings is not. So number of body piercings is no longer significant because the true variation in someone's weight is actually being explained by gender. And if you see gender male is what's explaining weight and reducing the sums of squared error, where number of body piercings was doing it, here it is on this slide doing it, having a statistically significant relationship due to correlation, which you could do a regression on. But if you want to isolate variation, you put the variables in the model, and if the variable has a low p-value, then it explains additional variation in the y variable with the other variables in the model, which is the key. It's like, okay, let's isolate what attractiveness does. And you see, this is what, here, can Brian do a mini rant? Let's have a vote. Yes or no mini rant for Brian? Yes or no mini rant? Everyone's like, no mini rant. Okay, then you guys asked for it. Okay. So one of the big things that just kind of like blows my mind is I'll see these videos where people will be like, a study controlled for this and this and this and this and this and this and this. And they found that the difference between males and females' wages was 2%, or maybe like 3%. And they'd be like, it was only 3% after they controlled for this or this or this or this. But here's the thing. If you control for everything else, if you control for like how long someone works, their specialty, their years on the job, their state they're located in, if you control for all of those things, and then you see a 3% difference, what does that mean? That means two otherwise identical individuals who have the same specialty, who have the same years on the job, who work in the same state, who have the same amount of kids, who have the same marriage status or whatever, widowed, whatever they are. If you control for all those other variables, you're saying they're otherwise identical, but one is male and one is female. The person who is female is expected to make 3% more. And I don't think they understand what the multiple regression means. It's very damning. I mean, they might say, oh, look, it's so much smaller. But that's, and the problem is too, it's across different industries. You have to look at each industry because the variation within each industry is different. Like if you were to look at the nursing industry, which I've seen data on the nursing industry, if you were to look at like engineering, if you were to look at different healthcare like pharmacy, there's going to be variation within each industry. So you can't say, because it's data is just so complex. But when I see these videos and they're like, oh, it's only 3% after you control for these, I'm like, then that means that gender is explaining 3% of the difference you see. And I think, I mean, could you imagine? I don't know. Brian's mini rant. But I just try to make data-driven decisions. That's what I do. And I look at the reports. There's a really good JAMLA paper, I believe, on the nursing industry. Maybe I'll pull that up. Like they show the confidence rules and everything, and they show what they control for. I think I need to end the mini rant with that. Let me see if I can find JAMLA nursing gender pay gap. What was it? It was 2014. Nursing gender pay gap study insight results. And then we'll do, I'm always like, go and look at Journal of American Medical Association, JAMA. This is it, I think. I think I found it. Methods, results, and then where's the PDF? Is this the PDF? Download PDF. I gotta sign in. No. That's well, I'm not gonna sign in to do that. We'll give this one more try here. I'm gonna Google some stuff in it. And then Brian's gonna stop ranting. It's officers and get to rant. Did I get it? Did I find the paper? Here it is, wait. I don't want to have to sign in. 10 more seconds attempting. Did someone put it online? That's such a bummer. I used to be able to just go straight to this. The graphics really show what's going on. It looks like it's a 2015. Well. Ooh. View on PubMed. Probably got to log in. Okay. Well, I want to read the research. Oh, wait. Here we go. Here's the figure. This is the figure I was looking for. Cool. This is the key figure I was looking for right here, which shows, here we can do 2H and 2I, you got it. So here is the, and if you look right here, what U word, here we'll hop over to the other one. You got a question, cool. What U word goes with these confidence intervals right here? What U word goes with these confidence intervals right here for the differences right here? You see they've got 0 right here, but we are noticing, and so what U word goes with these confidence intervals right here? Which you can probably tell because this is senior academic, and that has really wide right there. So there's probably due to, they talk about their, like this is what they control for, I believe. Not unique, so it'd be uncertainty. So we're looking at, these are confidence intervals right here, and due to variation within the data and probably due to sample sizes. And if you look, these are the differences they observed, and then the study goes through how they controlled for all these things. But I just try to read the literature. I try to make data-driven decisions, and so I think that's the best thing we can do. And once again, this is such a complex topic, but I just, whenever I hear people talk about statistics, I hear so much misuse of statistics, and I hate it. Oh, so I hate the misuse. Don't wait. We'll stay on the screen. Don't misuse stats. So 2H and 2I. I think did Alexa, did you have a question too? Alexa, post yours again. If you did, we'll hop over to 2H and 2I. 2H and 2I. Secret academic has an interval almost as wide as that. I know, right? There's a lot of uncertainty in that one. I don't, whatever they do, maybe the sample size was like 1. You can't even really build, you'd have 0 degrees of freedom, so you can't even build a confidence interval from that. Loud noises. Let's continue on. We got here 2H and 2I. Okay, cool. Out of curiosity, let's see how well each of the 3 models did on the holdout sample. So you have to use the post resample code from Caret, which will get you how they did. And then this is just going to see how the code did. And so Andrew was asking about this earlier. You can see right here the post resample. So let's go grab it. And here's the code. Now you have to do a light little change to it. We're going to have to change this up a little bit. Homework. There we go. Let's go grab it. Let's go here. And, oh, was this where we were? Okay, this one we were doing stuff with. There's the holdout. Okay, cool. So this is the actual and the predicted. Cool. So you have to put your actual right here. You have to put your predicted. What was it actually, and what was it predicted to be? But that's not the predicted. Is it predicted and actual? I think it's predicted and actual. Let's find out the hard way. So that's predicted, and this is actual, but we need to put in the values right here. So the predicted values are going to be from the predict, and we have to predict using our model, which is our GLM, I believe. And then we're going to do on new data equals holdout. I think we've done everything right there. And then the actual is going to be the holdout, and we need to go to, we're predicting next year's wins. Okay, cool. I think that's got it. Well, there we go. Is this, yeah, look, there's the number we found earlier. And so this is how the code works. I'll drop it in the chat here, but break down the code to its parts and take a look what we have here for the first argument. The first argument is your prediction. It's in the chat, so if you'll want it right there. And the second argument is the actual. So once again, this is just going to take what the thing actually is and what the thing would be predicted to be. You can also confirm this by going here and taking a look at it. These are just predictions. How does the predict code work? It uses your model. The predict code says, take my model and make predictions on new data. That's what it does. And then right here, the holdout, this is just a vector within your data of the wins that are the holdout vector. Does this all make sense? We should have equal length vectors too, which we do. So you can see that's the structure. That's pretty interesting. So that's got that right there. Hey, what's up, Madeline? And so the big thing, Andrew, is we want to see if it's overfit or not. What does it mean if something's overfit? What does it mean for something to be overfit? Like, what does overfit mean? Like, what does the literal idea of overfitting a model mean? It works way better on the what? What is the idea of overfitting? Like, if someone's like, I like the idea of overfitting. You're like, no, you shouldn't like the idea of overfitting. It works way better on the holdout. Exactly. And what's confusing is, and we saw this earlier. What's up, Ishan? And we saw this earlier that the model actually has a miss of 3.10 on the holdout, and the validation had a miss of 3.525. So when you look at the ratio of these, it actually does better on the holdout. This is not overfit. It's the weird scenario where your model does better on new data. So that model is not overfit at all. It's not a good model, but you should not. Nope, you don't have to set seed on this because this does not do a randomness procedure. So you guys are awesome. And then this one right here is not overfit also because it's only doing 3% worse. So when you look at this right here, we're saying like how much worse does our model do on new data? This model actually does better on new data, and this model right here does only a little bit worse. So all that right there. And 2i, you should find that the optimum value of alpha was 1, which corresponds to lasso, and you should find that this right here, the only value of alpha that corresponds, print to the screen, da-da-da-da. And so we're doing the GLM net. Okay, and then with the GLM net, let's see here. Don't worry, it's an exclusive. Oh, this is, okay, I know which one this is. Okay, so we do have to make our GLM net. Do I have that currently up? Let's grab this code. Cool. Okay, so we've made our GLM net. What does it say in the question? Oh, it says to set seed. Well, we don't have to. I don't think we do. Yeah, we shouldn't have to. Oh, for the nearest neighbor. Okay, no. For the nearest neighbor. Okay, whoa, yeah, sorry. Yes. Sorry. The nearest neighbor, the k nearest neighbors needs it to break ties. Yeah, sorry. That is correct. Sorry. I was thinking only of the linear and the elastic net. Those don't need it. The linear model and the elastic net wouldn't need it, but the k nearest neighbor for the breaking ties need it. Yep, sorry about that. Ryan made a mistake. Don't worry. And so when we look at 2i right here, this is really good. It goes back to 320. When we talk about models, which we were talking about models earlier today, and I've still got it up from when we talked about this at the end of class, to have a coefficient of 0 means that the variable has what impact on the model. Like if high school GPA had a coefficient of 0, then what would that mean? Like if the estimate here was 0, explain in words what it means if high school GPA had a coefficient of 0. Hint, the p-value would be all the way. Well, the t-score, I can figure out the t-score and all this from here. The t-score would be a t-score of 0, and the p-value would be 1.0. Yeah, it's completely insignificant, which is the lowest t-value we could get. Like when you standardize the metric, it's the absolute, great job, Jordan, 1,000 points right there. It's the most insignificant possible. So with a t-score of 0, it's completely the lowest standardized version because the t-score is just a standardized metric, and so it's the smallest, least significant thing we could have, as noted by the p-value right here. The estimate being 0, it has no impact. Because think of this mathematically, 320 if you're watching. If you were to change high school GPA, what would that do to this model right now? If you were to change high school GPA, like if I was like, oh, high school GPA is 1 or high school GPA is 4, what would this do to the model if its coefficient is 0? And Jordan kind of said it right there. It's going to have no impact at all. So it doesn't matter if its coefficient is 0. That's the least significant. You could say, oh, it's this. Someone has a ridiculous high school GPA, but that would have no impact on the model now. So that is what it means to have a coefficient of 0. And we see right here that, let's take a look. Wins, or was it wins we were doing? Wins has a coefficient of 0. I think I have the right model in here right now. Maybe my data, I feel like that's a lot, but maybe it does print out that much. But yes, wins has a coefficient of 0. So wins does not have any impact on this model. It zeroed out a lot of coefficients, unless I'm going mad. What coefficients did it use? Must have been a very small model. Let's see here, as numeric coefficients equals. Well, there's the ones it used, apparently. There we go. Is that right? So then previously, we should not see 2 in here. Yeah, there it is. So if you notice what I did was I switched the code for the coefficients not equal to 0. So I wanted to see the ones that's actually using. Question for when you're done. Sorry, no, don't worry. But, use 2019. And tell me if anything's weird on the grading. Tell me if anything's weird on the grading. Sorry about that. I should never update stuff. So that's when I tried to update something to 2020 and I just can't type. Yeah, probably use 2019. Just tell me if the grading's weird. The sanity check doesn't work. Use the one that meets. Which one is this? Let me search for it. 2019 0. Oh no. Okay, let's take a look. Did I do that? Steve Urkel. Did I do that? Can't do a Steve Urkel impression. Okay, let's take a look. Homework 342, homework 9, number 1. 342. Sanity check part A. Let's see right here. The AUC under the ROC curve is often used in business analytics, blah, blah, blah. The numeric values of the AUC can help us interpret as follows. If you're random, class of yes. In this problem, you'll write a function called pairwise AUC. Yeah, we did this. Yep. And feel free, or we've done this, and we'll keep looking at it right here. Oh. I think, here, wait, Alan. Put this in here right here and keep it the way it is, because I think you have to have that at the start. So I think, and don't we have the sanity check here? So I think you have to have that. So do you have this at the start of yours right here? Do you try running this and then see if that fixes it? Because that's, I think, the issue. Yeah, so use it the way it is, and then, yeah, so don't change it. Sorry about that. It's yours is probably set differently. Yeah, and Jordan found this also. What's up, Caleb? Hey, what's happening, man? So good to see you. Caleb, sitting on the left side last semester, right? I know exactly who Caleb is. I'm pretty sure. Left side, second seat from the end. Look at that, we fixed the problem. Boom. You sat next to John, right? I wonder how John's doing. Last I heard, John was like setting up, like, John worked like at a local, like, he was working in the kitchen at a local place, like sounded like a really cool, like local, like, you know, like, what's it called? Restaurant, but more like homegrown stuff like that. And he was setting up his own, I can't think of what it's called, garden. He was setting up a garden with him and his girlfriend, and his brother, I think. So I hope everyone's doing well. I hope you're doing well, Caleb. How you feel free? Tell me how you doing, Caleb. And feel free 320-474 ask questions. Yep. Oh, thanks, man. Thank you. You know what's crazy? And I thank everyone. I've been on like a roller coaster because like I am moving in 9 days. 9 days from now. Oh, cool. I'm glad you're interning with Caterpillar. That's awesome, man. Congratulations. Caterpillar's a great company. I am moving in 9 days, and I have not stopped since last semester. I went through mini-term. What's up, Ahmed? Good to have you here, Ahmed. So I went through mini-term and now, and I thank everyone. Because, I don't know, some days I wake up and I drink 2 Red Bulls. Oh man, I appreciate everyone. We've been working really hard. We got this. We got this, team. We got this. Yeah, let's do it. Let's do 3B, 3C. Let's talk about this right here. You ready? Okay, so we did this. Oh no, support vector machine. Stop. Don't do that, support vector machine. No. Okay, we should have never put in that support vector machine. Okay, we're gonna let it. Okay, we just broke it. Where's that support vector machine? Okay, this was a bad idea. Don't put this in your assignment. We just did it for fun, and we're going to break things. Block commented out. So all this right here. Awesome. Anytime, Caleb. Anytime, Caleb. Thank you so much. Just switch the 0.8 to 0.7? Maybe. I don't know. Let's find out. Well, it should be working, right? Okay. So, okay, we're good. All right, let's run all the code above. It's going to take a while. Just letting everything run. Cool. Okay. So this code right here is the code we did to standardize the variables. And please note that when you run this code right here, please make sure that if you were to check the min of this, what should the min of this be right now? Oh, I don't think it's an error. I think it's a warning. Does it say error in front of it, or does it give a warning? I think it's a warning. I think it's a red message that's a warning that's like, hey, did you know? Yeah, I think so. I think it's a warning. And this should give us 0 right here. I think it's a warning. What can I think? Yeah, it's a warning. So it's just being like, hey, did you know this? And it's all right. No, don't worry. Like, I always look at it too. Warnings appear in red also, but they're just warnings. So what didn't work? Let's see what we're talking about here. And let's overwrite these columns right here. We got those overwritten. We're going to check the sanity check, and we have the sanity check. So that's also what, yeah, no, good job, Ahmed, right there. Great questions. And we have the sanity check. Split the data into 70, 30%. Use the seed 2019 to find the fit controls that the AUC will be computed. So this is where it's the class factors summary. And let's go back here. And it's 2-class summary. So it's right here. I'm going to drop it in the chat. Once again, I just copy paste from this. I you know, you could practice writing it out, but I don't want to write that out. I'm always afraid I'm going to make an error when I write that out or try to. So we're going to go back to here. We're going to drop in this. There's the fit control. So once again, no need to write this all out, but you can see how it works. There, really? Okay. There we go there. Okay, cool. I like to make everything. There we go. Much easier to read now. Method is cross-validation. Number is 5 for 5 folds. Summary function, 2-class summary. Why is this? Well, actually, the class probs equals true, if I am correct, is what's going to make it categorical. So class probs equals true is what makes it categorical. The only difference here is you see the summary function 2-class summary. And so you have to, if you are doing categorical, you have to have this. But what will this fit on right now? What will this fit on right now? What will this fit on right now? This right now will fit on what? What will this fit on without summary class, 2-class summary, summary function, 2-class summary? Because we can fit on one of two things, at least with what we do normally with our procedures. I'm sure there's ways to fit on other things if you really wanted. What will this fit on? Any ideas? Hint, it won't fit on AUC. It'll do a regression. But remember, in regression for quantitative, we fit on RMSE, and we're going to be predicting, we're going to be predicting not a quantitative. We're going to be predicting something different here in this. We're going to be predicting purchase. So since we're predicting purchase, this is going to be a logistic model. So that's the key right here, is this is now going to be logistic with us predicting purchase. And so we could fit using this, but we won't. This would fit on accuracy, and now this will fit on AUC. So now that we have it written this way, the model will fit on AUC, but if we removed this, then it'll fit on accuracy. It'll try to optimize the accuracy, but we want to do it on AUC. So you have to have that additional argument. And then when it makes the model and fits the model, it'll optimize the validation on the AUC. So this optimizes on AUC. Very important what that does. Huge thing. 70% train, cool. And, you know, this is classic code writing. Train.rows. And we go set seed. And we want to go from 1 to the number of rows of, what's our data frame we're using? Account. And once again, copy paste your best friend. So all this does is this creates a vector. Oh, what am I doing? Set seed. What seed? Oh my gosh. Oh my gosh, the coffee wore off. There we go. We'll set seed before it. Oh, Andrew, you're so nice to me. And we want to sample 70%. I think this has it, right? Times and row account. And then we want to put before this the set.seed. I'm going to steal your set.seed. See, you help me out here. Right here. We got this. Look at this. And then we put the set seed before it. And this creates the train rows. So we're controlling the randomness. We get the same result every time. What did we do? It's mad at us. Let's just take a look at what we got going on right here. My gosh. There we go. I wrote subset. It's sample. And so we do have train rows. You want to confirm what you get. It's just numbers. So when we go here, we want to go to train, store into train, account. We want to take from account what? The rows that are in the train rows. And then you double click, you copy, you paste. And then you go here, you go to the holdout. And in the holdout, you want not the train rows. And there you go. Just practice writing it. Just kind of understand the theory. It's like, okay, I want the train rows in here. I want not the train rows. The more you practice it, the better you get. We check the head, and do we have it? The first things are correct or wrong. We find out. Oh, wait, that's still the... Wait. Did I not run it? There we go. And so there it is right there. We got it. And did you get it, Andrew? Is it looking good? Did it produce the same output for you? Good. Good. We've done it. The response? What does the response want for it? What does it ask? What does it want to know? What is the naive model's accuracy on the training and on the holdout? Ooh, good question. 320 question also. What is the naive model's accuracy? What does the naive model do? We talked about this today a little bit. What would the naive model do? What would the naive model do? I have a guess of what the naive model would do. I need to confirm it better, though. What would the naive model do? How does the naive model make predictions? Like, there's 1 drop of coffee left. Now there's no drops of coffee left. What does the naive model do? Hint, I'm looking at this right here to get an idea of what it would be. I've got an educated guess on what the naive model is going to do, but hint, something level, something. Yeah, exactly. That's Jordan's 100% right. So we need to find out what the majority class is, and I've got a good guess that it's no. And so what we do right here is we'd go to, you could do a summary. Summary works just fine. And train $purchase. And probably what we want to do is, no, wait. So what I'm doing right now is I'm finding the fraction right there, and I'm going to round it, hit the caps lock, and that exits that function, and then, no, I want to go by 4. There we go. Okay. So this right here is the percent of time it is no, and the naive model's accuracy. Does it want the naive model's accuracy? Yeah. The naive model's accuracy would be this right here. Naive model gets it right 65% of the time, and that's on the training data and on the holdout data. Here, I'll drop it in the chat. Hints in the chat. And holdout. And that's the holdout. And if you look, since this is randomly selected data, the naive model would be right 65% of the time on the trained data, and the naive model would be right 65.68. Like, it's randomly selected. So the naive model just predicts the majority level. Why would we predict no? Even though in logistic we predict yes. Like, every probability that this model puts out would be a probability of yes, but the model predicts everything is no because most things don't make a purchase. Does that make perfect sense on how the naive would make predictions right here? And the naive predicts the majority level in categorical or logistic, which logistic is a categorical Y. Who's with me on that? This is good Divian review for 320, and we're just doing the advanced versions right now in 474. So it's really good practice. And although arguments could be made for both metrics, explain why the bank would likely prefer to have models that tune for AUC. I need someone to explain fully, because I think the bank is trying to, what are they trying to see if people will purchase? Customers of a bank and whether or not they will purchase into a new type of CD account. So what is AUC going to optimize for these customers? I'll let you guys explain to me, chat. They're probably more interested in customers who have the highest probability of purchasing. Kind of. And you're right. That's what you're getting to the point of AUC. Like, you're basically there, because think about this. If the bank has, how many customers do you think Bank of America has? How many customers do you think Bank of America has? Just a guess. I mean, maybe like, what, 5 million, 10 million, 20, 30 million? I mean, millions, exactly. So if Bank of America is looking to send out a promotion for doing CDs, then they might only want to send it to people where the people they send it to, like, if they choose them, that person has a very high likelihood of doing it. And the way in which AUC is optimized is that it tries to put 66 million. That was right there, Andrew. AUC tries to optimize so that the people with the highest probability, the yeses are properly ranked. Like, the yeses are put at the top of the model. The yeses get the highest probabilities. Does that make sense from what we've been saying, says Google? So AUC, like what would really hurt in AUC? We talked about this a lot over the last few days as Brian like had a crazy Wednesday. When you talk about AUC, if you have something like this right here, and it's not a vector really, it's just me typing numbers for the moment. If you have something like this, where this is yes, this is no, this is yes, and this is no, the accuracy here is going to be 75%. So the accuracy here is 75%, and then the AUC for this would actually also be 75%, because this yes is higher than all the no's. But watch this. We could have this right here, and now, and so we could change this. Let's just make some changes. Let's go here and do that. And so when you look at this right here, this model now has an accuracy of, sure. This model's accuracy is 50% and its AUC is 50%. I gotta stop having ones that have identical. Oh, here we go. This will switch it. Now they're different. What is the AUC of this model? 1,000 points first person. What's the AUC of this model? Like you could flip the classes, but it's by calculating what the yes class is. And the accuracy of this model is 50% still, because it's 50% accurate on how it makes predictions. These are horrible models. The AUC of this model would be, I guess technically you could predict no. It's, yeah. It'd be 75%. Yeah, or 25, because you could just flip your predictions. That's the problem with this right here, is you could flip these to be like this, because the model would in truth kind of do something like that. So it is kind of like 25, 75. It's just kind of flipped. And the way I had it, I think you're right, Jordan. What am I doing? Did I say you're wrong? Because it is 75 or 25%. Sorry, I'm just juggling numbers in my head as I'm talking about this. But the yes class receives a higher probability than the no class 25% of the time right here, because this is only 1 out of 2 times, and that's 0 out of 2 times. So models like that don't usually exist, though, because it'll reformat your yeses and nos. What is the AUC of this model right here? What is the AUC of this model? And you see, now we're starting to get better. But what's interesting is, and so this model has an AUC of 66%. This model has an AUC of 100% or 1, because the yes class always receives a higher probability than the no class, and thus we would kind of go through all the yeses first before we get to a singular no. So when you look at how this is optimized, if we optimize on AUC, it's going to try to put the yeses at the top. Even though this model incorrectly predicts this individual, it still has the yes getting a higher probability than the no. Does that kind of make sense, Jordan? Like when we optimize on AUC, it's not going to look at this and say, oh no, we said that this person didn't, the probability is below 50%, so they're predicted no. It doesn't care. It's like, okay, they're ordered correctly. That's what we want. So it's going to focus in on putting the yeses to the highest probabilities. Like it's going to try to stack kind of the top of the deck of your probabilities with yes, 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 yes. So when it tries to optimize on new data, the things that have the highest probabilities are going to be at the very top. So what really hurts it is when a no gets shuffled in up here. Like if a no gets a very high probability, that hurts it way more than just being 1 inaccurate. Like this doesn't harm AUC at all. AUC is like, yeah, so what? We ordered them correctly. Because AUC would not care about this until this went below 15%. Then it's misordered, because the no would have a higher probability. But right here, AUC is still 1, AUC is still 1, AUC is still 1. AUC is still consistently 1 right here, because the yes has a higher probability than the no's. All yeses have higher probabilities than no's, and that's what an AUC of 1 means. If you can't tell, that's the main focus of like what we want you to know about AUC. It's like, it's how we order the probabilities. It's that the yes class receives a higher probability than the no class in the percent of time. So the higher the AUC, the better you've ordered your probabilities. That's got it. Using the train fit vanilla logistic. So we basically have this. And we got Sandy check, GLM net grid. There's the GLM net grid, nearest neighbor. That's so easy. Aw. Which of these three models did the best on the holdout? Proc, post, resample. So I think pretty good right here. What? They get broken? Yeah, so make sure to do the, yeah. From here, it's just using your repeated code. That's why we say, you know, like if you have the code written, you're pretty good on it, because the code we have right here, especially with the k nearest neighbor grid, I guess we're using this again, I think. And here's our GLM net, and I think we're using the same alpha sequence. So we could literally just take this code for the GLM net grid and go down to here. And here, let's put it in here. I think at first I wanted just regular old. So that's GLM, remove the grid, change this to purchase. And we technically don't need the grid till later. And so let's move it. GLM net, it's running, takes a little bit longer. Accuracy was not used, good. And, oh, did I sort it into GLM net? Oh, that's a bummer. Okay. So we should see the results in here. Let's go to GLM net, GLM results, and there we go. There's the ROC. And was that the values we should? Yeah, we got the right values. Is this making sense right here, what we're doing? And if you notice, once you have this code written, all you're changing is your Y variable. Does the code for train seem pretty easy, Jordan, Andrew? Does it? Because now I can just change it to GLM net grid. If I really want, I can go here. I'm just going to rewind time on it and make that appear. And then I'm going to put this code here first. And I can put GLM, oops, GLM $ results. And there's that. Then here's my alpha grid. And purchase. Yeah, it's pretty much copy paste. I mean, that's why you see me doing it all the time, because, and I think that's got it right here. Error, the tuning grid should have columns parameters. GLM net grid. What's it meant about? What is it meant about? Oh, ha 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 ha. There we go. I changed that. Yeah, exactly. Once you have the format and you have the document, it makes it easier to read. And so we're just making the GLM net grid right here. Now, when you do this with the GLM net grid, you want to look at your results. You're going to get a lot of results, but you want to look at your best results, which we should have the best. There's the best tune. And I'm going to go here to row names. So the row names, now you could just type 5, like, but we don't want to type 5. We're actually going to like go in here and grab this row names right here, go to the GLM net, go to results, and we're going to go here, do this, and run this. So what you could do, see, I wonder if there's a way. There is a way, I think. There's things that I know how to do, and I'm so close. Yeah, vanilla regression is just GLM. GLM net is regularized regression. It's elastic net regression with lasso ridge. And so the lasso ridge is right here. This is the mixture of lasso ridge. And the lambda right here is the regularization penalty. So it's important to know what each thing is doing. I can't stress enough that don't just write this code as though you're just like, I'm just writing code. Know what each thing is doing. This makes the grid of values we are trying, and you can plot this. I don't think it says to plot them, but it's nice to plot them and see what you got going on. So if you go to plot GLM net, you can take a look at it and see what values it actually ran through. So if you look at the values, it's looking at, you can see, wow. So we're looking at ROC. We want to optimize ROC. So in truth, we want to go over here. And you see, probably need to make it finer. There's something going on in here. So I would actually look at the regularization penalty. Like if I'm going to narrow this down, I'm going to go between 0 and 0.01, 0.02. Like if I'm going to redo this, I'm going to go back to my GLM net grid. So how do we see how many models are tested? Oh, so yeah, do GLM net grid. I don't know if I have mine set up properly, but 35 models were tested. I don't know if I have mine set up properly right now, but there were 35 models tested. How you could multiply out here. Here, I'll look at how many were tested for this one. We're supposed to use a sequence from 0 to that. That looks like 10 numbers. No, it's 11 numbers, right? And then use powers going from here. So that's 0 to 1. So that's 11 numbers. And then 1, 2, 3, 4, 5, 6. I think you should have 66 models. I'm pretty sure it's 66. Do you see 66 when you do yours, Jordan? When you double click GLMNet grid, you should double click it and you can see how many rows are in it. And you should see 66. I'm guessing because it looks like there's your values of alpha go from 1 to, by 0.1. That's 11 values. And then your sequence, I believe, is still the same. Let me see if that's the same sequence. What did it not like? I didn't put my comma right here. Oh, I have too many commas. There we go. And let me double check. 77. I think I have one too many. Where are we going? -3 to 0.5 right there. Okay. So -3. -3 to -0.5. And this should make an expand grid of 66 from what I'm guessing. Yep. And how did I know that? It's just there are 6 values right here. And then there are, no, it's not 6. There's 11 values right there. And then there's 6 values right here. So there's 11 values times 6. 11 times 6 is 66. This is like the pizza topping thing we talked about, or making pizzas or cookies. This is just how many combinations there are. Yeah. You don't want to do length. You want to do n row. So if you want, you can do n row GLMNet grid, and that'll tell you how many. The length will get you 2, right? For length, you got 2, and that's how many tuning parameters you're using. So the length would be the amount of tuning parameters, and the rows would be the numbers of combinations by which we can make models. But good, yeah, great questions. We should know what these things mean. Like, that's it. Like, yeah. And yeah, so we'll get a totally different model here now, which would be cool to look at. Let's look at it. Let's look at this new model. Let's see what we get. Who knows what we'll get? The best model is, it's working away, doing a bunch of work. Come on, you can do it, computer. Really? 66 models? Cool. And there's the, whoa. Took a jump right there. And it looks like it's picking an alpha of 0. So the alphas are a mixing percentage. And so it's showing, here's the mixing percentages. Okay, 0 mixing percentage. And then the lambda it's picking, the lambda is 0.01, so it's the blue line. It's very hard to tell. The ROC is 0.66, and that's where we're hitting somewhere in here. So it looks like that. There's the best model is the, mixing percentage of 0 and the blue line. So it's right there. And it looks like they all kind of converge right there. If we looked at the models, which we could look at by going to GLMNet, results, and we could look at them right here. And oh my gosh, look at all these results. Too many results. And here we go. So all of these alphas of zeros, yeah, they're tied. They're all tying, and I mean those 3 are tied. So yeah. Oh, and then here we go, right here, right? Was that the one? No, or is that tied? Oh, it's just barely lower. But I mean, like, if you look at, so it gives you sensitivity and specificity and everything. But if you look at, oh, really? Cool. If you look at the uncertainty in these models, they're all going to be very similar. So here's the best models with the best ROCs, but if you look at the ROC standard deviations, they're all very, very similar. All models within here are basically the same. So 66.3, and that's about 1%. So it's basically down to 65. So if you look at the graphic, every model across here does about the same. Does that make sense, Jordan? That within the 1 standard deviation would be probably not that model. All these models here, basically every model above this line-ish, like above here, all these models are virtually identical. So it's like they're all about the same. So they're all good models, but you don't want these models. These are horrid models. Yeah. Every model from about here above is about equal powerful. They're within 1 standard deviation of each other. It's like, I don't know. And you get more interesting graphics sometimes. You can do crazy things if you want. Like you could go, and I mean, if this was your job, you could go in and be like, okay, let's narrow down the field inside of here. Like I'm going to go and I'm going to be like, let's narrow down this area. And it looks like it's mainly going to be that. So I want to go to my alpha, let me see here, my lambda. Is that, no, my mixing percentages. I think that's what's going to optimize it. So let's go to my mixing percentages, which is going to be my alpha. And I'm going to narrow down the alpha. I'm going to go down here to 0.2. And I'm going to do this by 0.02. And next year's wins not found. Oh, okay. Go down. Oh. Purchase. I can't spell. All right. You can tell Brian's. It's the weekend. It's the weekend coming up. There we go. So we'll let this run here for a second. We'll take a look at the grid here in a moment, see what we get. And we'll only see up to 0.2. I just kind of want to narrow down this region and see if there's any, like, we'll get a tighter view because it's only going to do points between this. And so now when we plot it, we can kind of get a better idea of what's going on. And it's a little bit cleaner of a graphic to look at. And, you know, all these lines up here are overlapping where we don't really see any differences. So, I mean, you know, we said 65 or above, but this is, you know, us just narrowing down the view, and you can see what the mixing percentages. So obviously we do want to go, is it all ridge? Whichever one it is. We want to go all this mixing percentage because it's generally dropping off. And we also want to go to one of these up here. So, and then you can just look at the best result. So now the best result is a lambda, an alpha of 0.02 and a lambda of this. And it's, you know, it's basically the same ROC we've been getting. So, yeah, I mean, we're basically, this is about the best that this model can do right here. Any other last few questions about what's going on? I think we pretty much got this all done. I mean, I don't know. It's, if you hopefully people are like, yeah, I kind of get what's going on. How do people feel about it? Andrew, Jordan, how do you guys feel about this? Do you feel like you're kind of getting how predictive modeling works, how we make these models and we test out all these different, like you just tested right here. I just literally went through and did, how many models did I create? Create 77 models. What does this do? That finds the best result for the k-nearest neighbors model. So that code right there is very similar. It looks like no models overfit here either. I think so, right? Yeah, I think so. I don't think, and we shouldn't usually see overfitting. If you look at your code right here, what this does is this goes to the results and it returns only the result of the best row. So it's going to go inside the results and return the best row. So when I run this on GLMnet, it tells me my best result, and I could do it on the GLMnet also. And all this is going to do is go inside and tell me the best result from that model selection. Does that make sense, Andrew? It finds the, do we need that on all the other chunks? If you're going to look at models and see how they did, yes. Anytime you're looking at models, and let me double check. I think you're right. Let me look at that. I think all the models are not overfit. Let me just look at the, I'll confirm if you like an answer real quick. I think they're not overfit because we got to look at the AUCs. And so how did they do on the holdout? Looks like we're getting like 65.18, 65.17. Ooh, 68. The K nearest neighbor on the holdout is 68.99. So yeah, what did the K nearest neighbor get on the original data set? On the original, 69.48. Wow. Well, I'm just going to drop that in here. Why not? Let's take a look at it. Let's drop the K nearest neighbor in here. So the K nearest neighbor, we got the grid for it. Are we appending all that? There's some code that's appended on kind of, oh, there it is. And then there's that. This is all, there's that. Just clean up the code real quick, make the code look nice. There we go, pre-products under scale. So this makes the grid right here by which we'll try them. And then right here, good, we're making the k-nearest neighbor model. And let's take a look, because this one apparently is pretty good. So I was like, okay, if it's the best, we'll take a look at it. Yep, that's fine. That's the warning beam printer right there. So this is the k-nearest neighbor model where things get to vote on what's what. And apparently it's going to look pretty good right here. K-nearest neighbor is taking its time, though. We're going to take the k-nearest neighbor results, though, while this is going on. We're just going to put it after it. Be very careful. My code is completely disorganized right now. Your code needs to be in order or else you will have problems. We're also going to plot the k-nearest neighbor which will show us how it works. So we called this k-nearest neighbor. Cool error message. We don't care. It's not an error. It's a warning, I should say. And what this is going to now plot is this is now going to plot. There it is right there. This is going to plot. Sure. It's going to plot the k-nearest. Wow. Ooh. Here's the issue. Yeah, it is. It is the best. It's definitely. Yeah. 55 nearest neighbors. What I would do is I would go in here, like, no, don't do this, but I would start looking. I mean, this is way better. This is because when you look at the AUC of this, and we also want to look at like here, let's do it. Let's go grab the code we have for that. When you look at the k-nearest neighbor results, the best row for it, its ROC standard deviation is 0.7, like as a percent. 69.48% of the time, we accurately give the yes class a higher probability than the no class, and our uncertainty is about 0.7%. So comparing this to the GLM net, which I think was the best before this, the GLM net was 66.3 with an ROC of this. So what you need to do is you need to take the two, subtract their difference, and once you subtract the difference, you divide by the larger of the two standard deviations, which I believe is this one right here. And that's their difference. That's worlds of difference. This model's predicted power is 3+ standard deviations above. The k-nearest neighbors is 3+ standard deviations away, and that's a standardized unit of measurement. So that's a lot because it's a z-score. So it's not performing 3 times better. Its difference in its predictive power is 3 standard deviations above the other model. And so there's a huge difference. The answer here is to use the k-nearest neighbors model. This is a open and shut case for k-nearest neighbors. Does that make sense, Jordan, why I'm predicting? I think so, Andrew. If you can include your one, tell me if you think the grader's too hard. The grader's been pretty nice, I think so. No one's complained about the grader yet. But there's worlds of difference between these two models. There's worlds of difference. So the k-nearest neighbors model is hitting a home run here. And so we'd be like, yep, k-nearest neighbors is where it's at. And then what you could do now is you could go and zoom in on the k-nearest neighbors and go from like 50 to 80 and go by 2. And there we go. So now what I've done is I've zoomed in on it. I'm kind of looking in that 50 through, I probably should have done like 40. But I mean, probably all these models are going to be so similar. We might see like a bend to it, but I'm wondering what we'll get. I just kind of want to zoom in on that area a little bit and do a little more testing. No, so it is better. The model is better at accurately ranking the yeses with a higher probability than the nos. Because of the difference in the AUCs we see mathematically, the mathematical difference between the AUCs calculated right here turns out to be more than 3 standard deviations. This 3 standard deviation difference is a very large difference because it's standard deviations, so it's a z-score, and a z-score of 3 is very unusual. So it's very likely that the model that has an AUC, which was the k-nearest neighbor here, that this model actually has a higher predictive power, a better ability to do well on new data than the GLM net. The k-nearest neighbor seems, we have good evidence to suggest, due to it being 3 standard deviations above the other model, its distance is more than 3 standard deviations away from the other model. Does that make sense, Jordan? So we have good evidence to suggest that the k-nearest neighbor model is going to be the best. So with this information alone, I would pick the k-nearest neighbor, and I'd want to see how the k-nearest neighbor does on the holdout, which it does really well on it too. And then what I did here is I went and looked in depth at that's interesting. And if you look, they all kind of do kind of well. It's just, it's so cool to see these things. And you see, here's where we were at with like 55. So what I did was, and I'll vanish again, is I did a k-nearest neighbor grid where I went up by 2 each time. And it's just cool to see the pattern you get from these things because it follows like a pattern. And it's going to suggest to me a k-nearest neighbor of 52 now. Like if I go to the best results, the k-nearest neighbor it's going to suggest is the 52 because you can tell right there. But all of these models are going to be very similar because the right here is 0.7. So we're not, these differences, Yeah, all of these differences are likely by random chance. This is just the really good region of the model. I don't know, somewhere in the 50s, and we could like, once again, if we really want to go crazy, we're going to go here to 30. We'll end with this because now we should see kind of more of a kind of bevying out at the top where this 50 hits, and we're going to see a finer grid to it. But it's kind of cool to like pull up these graphics, take a look at what's going on here. But because the standard deviation of the ROC, which is our uncertainty, this goes back to 320, our uncertainty is 0.7 or 0.007. And so all of these here, do you see how the number line here is only about a 0.2 difference? If you go up to the very top, to the very bottom, it's only about a difference of 0.2 or 0.002. So the uncertainty within these estimates is all these models are basically equal. All these models have about equal predictive power. So it wouldn't matter if we use a k-nearest neighbor of 50 or 52 or 54 or 56 or 58. They're all about the same. Actually, I heard the fan turn on. It's thinking over this k-nearest neighbor. Is this making sense, Jordan? What's going on right here? Like how I'm just kind of refining my k-nearest neighbor grid. This is not part of the assignment, but it is part of how we do predictive analytics. Like if you want to like reevaluate, because there is no right amount of k-nearest neighbors to use. You just kind of pick and choose and make and do, and that's predictive modeling. But we can't say like just come up with your own grid, because what if someone came up with like 1,000 numbers? I mean, you could. Yep. And so we'll see what we get right here. I like looking at the patterns. This one's kind of boring because it only has one tuning parameter, so you don't get kind of the cool like multiple line patterns. Oh, it did it. And then let's take a look. There it is right here. And this is what I was focusing in on. The kind of important spot was right in here, even though if it's 0.7 though, then these models are still similar. I'm still going to pick in this area though, like 50, 52. This is fine. And it's a different graphic because I think it's using a different procedure, and we're just chewing away. It is, my original thought process was, since it's far off from the others, it was bad. It's good though, because remember, we want high ROC. We want high ROC. So the higher the ROC, the better. It has way more predictive power in such a way that it is a lot better than the other ones. It's like way better. And I think that's got it. Any other last questions? A lot of great work today. Kind of covered a little bit of 320, a lot of 474. Good stuff today. Coffee's done. It's already 6 p.m. What happens to the day? You're welcome, Jordan. Excellent work. Keep it up. Keep just, asking questions. Can we all... You got it. Just keep working on it. You got it. I mean, did you finish the assignment, Andrew? Are you done with the assignment now? Like on a scale of 1 to 10, how hard was this assignment? You guys got this. You got this. You're doing well. You can do it. You can get the A. You can do it. I don't know. I'm not saying you will, but I want to see you guys got the hard work, and I gotta finish up I might put out the take home tomorrow. I gotta finish it up. 7 out of 10. 7 out of 10 is good. Yeah, it's a senior level class. That's good. 7 out of 10. I like that. I think that's very good. And you understand a lot better. That's good. Yeah. And they're very detailed assignments. Coding, interpretation. Yeah. Interpretation is the hard part. The coding gets easier. And I tell that to 320 students all the time. Sorry, 320. I'm like, it gets easier. I swear the coding gets way easier. By the end of the semester, you're like, coding. Coding, that's not the hard part. Oh, interpretation. We got to actually explain what it's doing. Here, I'll type it. But what does it mean? So that's why we do business analytics. Is it's not just about writing the code. It's like, okay, what does this graphic tell us? Okay, this graphic is trying to optimize the ROC, which is the way in which we give the yes class, trying to give the yes class a high probability than the no class the percent of the time we're doing that. And the better you get at interpreting this, the better, you understand the topics. Of course, you could be like me and just make mistakes and not know how to do your ROC one day. It happens. But with that said, we're going to head off right here. Thank you, everyone, for being here. And I'll be finishing up take-homes. I might be able to get them out tonight. We'll take a look. But I will talk to everyone later. Bye. Have a great weekend, everybody. Bye.